Okay, hello again. Well, let's continue with this topic. In relationship to dependability, I mentioned already it's dangerous to use complex systems and complicated systems. Complex systems because they have so many components. And if one of these components fails, then the whole system is going to fail. Therefore, complex systems or complexity is dangerous when talking about dependable systems. On the other side, complicated systems, these are such systems that are difficult to understand. Maybe they don't have to be complex, but maybe they are wrong implemented. They are implemented in a very complicated way. And if they are difficult to understand, then they will be for sure, but implemented. And then for sure they will fail. And now let's talk a little bit more details about this. Some of these things I mentioned already in just a second. Okay, some of these topics I mentioned already in other videos, but I'm going to repeat it in a very short way. First, maybe do you remember the history or the development of embedded basic systems? Let's take, for example, an operating system. At the beginning, the first version of the operating system is always very small. And this is the rest. That is the application which you are going to have. Okay, the operating system is there to help you for your application. But your target is not to have an operating system in your embedded system. Your target is to have your application running in the operating system. So the main part, where is, just a second please. Okay, I am back. Okay, the main part of your effort is your real application. This, let's assume this is your real application. Okay, for the first version it will be nice. For the next version, people will continue adding more functionality to your basic system, for example, your operating system, and then your operating system will grow and grow and grow. And after every mission, your operating system will be bigger, more lines of code, more effort, and so on. And not only operating system, all libraries which you are using to implement your application, which is the most important. And after a while, the overhead you have to transport is maybe bigger than your real application. And if this continue, if you don't stop, then it's going to collapse. Okay, and then the overhead, what was at the beginning only the help, is bigger and heavier and requires more effort than your real mission, which is here, already collapsed. Let's summarize. If your operating system or your basic system has more lines of code or is bigger than your real mission, then you have a problem. Let's say you have a complication. You have done something wrong. Do not forget, this was not the main part. This was not the main mission. This was just to help you. And at the end, it was bigger than your real mission. Okay, this is one problem when it is going to collapse, when the complexity keeps growing and growing and growing. This was the target at the beginning. Okay, if you compare the lines of code of different systems, for example, to go to the moon and come back, they need only, let's say, 150,000 lines of code. If you compare with this Clippy from Word, from Microsoft, it has 100 million lines of code. Just compare. And what is the functionality of this and what is the functionality of this. But as you can see, as the time is going, the complexity is growing and growing and growing, and it doesn't mean the functionality is higher. It doesn't mean it's getting better. I think it's getting worse. Okay. And why do we have this situation? At the beginning, you have an original design. This is what you were supposed to do. When you create your system, first make a design and it's implemented in an optimal way. But then new missions, the time is going, new requirements come, and then you have to add functionality. And when you are adding functionality, for sure you are not going to update your design. You are just adding. Okay, the first time is okay, but the second time it's getting worse and worse and worse, and at the end you get something like this, really fat. And where is your design? Your original design has disappeared. Now you don't have a design anymore. You have just added and added and added functionality. And this is the reason why we have this situation from here to here, because you don't make a redesign, you just add functionality, and this will bring the collapse. It will not be working anymore. Okay, what to do? What we can do is, okay, if we have to add functionality, we shall try to find what we don't need and remove this older functionality and keep the design. Every time you make a new functionality, take a look to the design and update the design and keep in mind the design of your system, not just adding and adding. And if possible, try to remove what you don't need. Well, this is really difficult. Like, for example, you have a soup, you add salt to the soup. It's very easy. You tell the salt, throw to the soup, and then you have more salt in the soup. Now try the opposite. Try to remove the salt from the soup, and you will see almost impossible. I don't know how to do that. So adding things is simple. Removing things is very complex, because you cannot see what are the dependencies. If you have some variables, you don't see what will be if you remove this variable, or if you remove functions. Are they required somewhere else or not? It's really difficult. Therefore, my warning will be very careful with adding things and try to remove what you don't need as soon as possible. Later will be almost impossible. Okay, and now let's come back to the complexity. Do you remember I said, if you keep adding complexity, coming from here to here, your system will collapse. And I'm going to show why. Okay, for every system you have to build, there is a margin of the complexity. Let's say this axis is the complexity of your system, and this is the fragility. And do you remember, complex systems are fragile. They are the probability of failure is much more higher than simple systems, because it's a chain of many components. And if any of them fails, then the system is going to fail and the system is going to collapse. Therefore, it's clear, I hope it's clear, more complex systems will fail with a much higher probability. And then let's say this is the complexity, and the opposite of dependability or reliability is fragility. So the probability of failure. And the probability of failure will grow exponentially with the complexity. And then we have two limits. Let's assume you have to implement one system, and then you begin here. And this is the current complexity of your system. It's working. If you keep adding functionality, it will reach this point where the complexity is too big, it has to collapse. So this is what we call the critical complexity. When you reach this point, the system is not going to work anymore. The only thing you can do is throw it again, redesign, and re-implement. You try to remove the complexity, will not be possible anymore. On the other direction, this is what we call the irreducible complexity. For everything, for every function which you have to implement, there is a limit where you cannot do it more simple. If you remove anything, then it will not work anymore. This is the irreducible complexity. Per definition, this function, it's not possible to implement more simple or simpler than that. Okay, then this is the target, the most simple solution for this function. And from here to here, you are increasing the fragility. And from here to here, these are self-made problems. And if you are at any point, then you can estimate what is the margin, how much complexity you can add before you come to the critical complexity and your system fails. Okay, I hope you believe me. I hope this is clear. And let's say this graphic, this is the maximum complexity when the system crashes. And this is the minimal complexity which you can have to implement this functionality, what we call the irreducible complexity. Okay, this is the zero complexity, and this is open end. This is the lowest complexity you have to implement for this system. This is your current complexity, and this is the critical complexity. The target shall come here, but the reality is normally, no one is trying to reduce the complexity. Everyone is adding and adding more and more complexity coming closer and closer to the critical complexity and reducing the margin under collapse. Did you remark this? If you want to do dependable system, then don't try to add complexity. Try to be removing complexity and making it simple. This is what we do. We have developed several mission critical and safety critical systems. We have a first implementation, and after this first implementation, we try to reduce the complexity and to make the new version more simple than the previous version. And this is really the opposite. If you take a look to any development, the newer version is more complex than the former version. And as you can see, it's coming closer to the collapse, to the critical complexity for almost every system which I know. And here are some examples. Many failures and accidents come from functionality and code which were not necessary. Do you remember this? Which I recommend. Try to remove everything which you don't need. This is a very famous example of the first flight of the Ariane 5 rocket. This was a failure, it was an explosion, and it was destroyed. And after making the analysis, what was the problem? The problem was an overflow in a software module which was not required anymore. This software module was required for the previous version of this rocket, the Ariane 4. But they took the software of Ariane 4, implemented in Ariane 5, and they said, well, if it works in Ariane 4, it shall work in Ariane 5, so we don't need to check it again. The problem was Ariane 5 has a higher acceleration than Ariane 4, and then they had a overflow in a variable which was never used. And this overflow make a memory dump of this module and sent information in the data bus which was not expected. And then the control system lost control, and then we have the accident. Very dramatic. For a variable overflow in a variable which was not used or required anymore, because just adding and never removing. Do you remember? Okay, just a second, please. And there is another important thing. The less code it has to be implemented and tested, the more perfect the system will be. The less code you have, the better and more time you will have to test this code. If you have a very big system, then you have too much to test, and the test effort for the critical parts of the system will be very limited. That's dangerous. Okay, and now let's talk about complexity and mental capacity. Well, we can talk about complexity or complicated systems, both come here together. This is for, I hope you agree, if you are making more complex or more complicated system, then you will need a higher mental capacity to understand the system. And I will say the required mental capacity to understand a system grows quadratic or exponential to the complexity. And there is a limit. We have to accept the mental capacity of every of us has a limit. We cannot understand everything, and we have to accept this is the maximum I can understand. If we accept this is the maximum which I can understand, then I have to accept this is the maximum complexity or complicatedness which I can handle. Everything beyond this point of complexity is something which I don't understand. And I would like to say why I say this grows exponentially or at least quadratic. Let's say you have many components. If you have, let's say, 10 components, then you have to understand 10 components. And then you need a given mental capacity to understand these 10 components. But if you make twice as much components, then you have 20 components, then you need at least twice as much mental capacity to understand these 20 components, but the difference is the components are not isolated. All components in a system, they are related to each other. And these relations, they grow quadratic with the number of components. So if you have 10 components and each is related to each other one, then you have almost 100 relationships which you shall understand. And to understand these 100 relationships, you need a required mental capacity. Twice as much, let's say 20, now you have 400 relationships between components. So it's growing quadratic. So the number of relationships is growing quadratic with the number of components. And you have to understand the components and the relationships. Therefore, you need here at least twice as much components, 4 times as much require mental capacity. So you have to be 4 times more intelligent to be able to understand a system which has double as much components. And we can continue. There are not only relationships between components, there are relationships between relationships of components. Then you have n squared, n plus n squared plus n to the power of 4. So this is growing very fast. Okay, and now you accept, I hope you accept, that the required mental capacity is growing really much more faster than the complexity. And I hope you accept your mental capacity, your intelligence has a limit. And then you have to accept there is a limit of the complexity which you can handle. And everything beyond this complexity is something which you don't understand. So if you are building systems with this complexity, you are building systems which you don't understand. And if you don't understand, you shall not wonder if they don't work. You shall wonder if they work because you have built something which you don't understand. And maybe no one of your team understands the whole system. Everyone is going to understand a small part, and the next will understand the next part, and there are holes. Just a second, please. There are gaps between these islands of understanding of person. And these gaps are very dangerous. This is the gaps, the things which no one understands, and the places where the failure is going to come. So it's very dangerous. The best thing is to build systems which everyone in the team is able to understand. Everything, not only the small part which the team, this person is building, but everything, all components. Okay, let's see some statistics. Here we have we have analyzed many different codes, many different projects, and we saw the lines of code of each of these projects. And then in time, we are counting how many faults we have or crashes. And we can see simple projects with very few lines of code, they have very few crashes. Very complex systems with many lines of code, they have many faults, many crashes, many bugs. And you could say, of course, twice as much lines of code, twice as much faults, twice as much, bugs. But it's more than that. Let's take a look to this. This is the module size. This is the frequency of faults, of bugs. So when they are growing, you are getting more and more and more bugs. So there is no surprise, more lines of code, more bugs. But maybe you will expect this is a constant. The number of bugs per 1,000 lines of code shall be a constant. So twice as much lines of code, twice as much bugs, but the relationship is the same. But if you take a look to this is growing. The number of faults or errors or bugs is growing with the lines of code. Small projects have less than 2 errors per 1,000 lines of code, bigger 4, 5, 6, and it's growing and growing. And if you make a line here, making the average of errors per lines of code, then you will see this grows exponentially. Maybe because this is the mental capacity of the programmers, and this is the understandability, the limit of the complexity which the programmers can understand. Until here, it's okay, and from here, when it goes beyond what the programmers can understand, then it grows dramatically, and then it will not work properly. The same reason. Okay. And what's the problem? You think you can create complexity, and you can have tools to control and manage the complexity. So Many people think, do not worry, make complex systems. We have the tools to manage complexity and to take take it under control. That's the problem. You are creating complexity and then trying to handle this. First, create the monster. I will say the complexity is the monster, and then try to subdue it, and it will not work. At one point, you will see you have lost control, and the monster, and you are inside of the monster until this will work, until the monster is stronger than you. And if you are adding complexity, the monster, which is the complexity, is growing and growing, and it will grow bigger than your mental capacity, and then you have a real problem. You cannot bundle or subdue this monster anymore. It's stronger than you, and it's the complexity. Okay, and now a questions. Do you know why so many complex systems do not work in a dependable way? Why so many complex systems fail? Do you know? The reason is very easy. They fail because they are so complex. And the most complex part in modern systems is the software. So we shall take a look to the software, and this is the first thing we shall take into control to reduce the complexity. And the software is, for normal complexity, for normal systems, much more complex than what any person can understand. So you need a team of 20 persons, and everyone is going to understand only a small part, but you will have gaps. And I said before, these gaps are the sources of failures. Okay, but you say there are good news. Now we have better software tools, better compilers, better analysis, static analysis, and so on. So our software is getting better. And this is a history of the time. That is the errors or bugs per 1,000 lines of code. At the beginning of the software history, you have many errors or bugs per 1,000 lines of code. And as time is going, people are better programmers. They get better instructions at the university, better programming training, better training at the university, better tools to find bugs, and then the number of bugs per 1,000 lines of code is going down. Every year we are improving, so we have less bugs per 1,000 lines of code. Well, there is a limit. We cannot come to zero, but it's coming asymptotic almost to zero. Then you can see, oh, good news, the software is getting better, so there is no reason to worry. Do you think there is something wrong here? Take a look. You are looking the time, years, errors per 1,000 lines of code. The errors are going down, so the software is getting better. But the reality is something different. And if you take a look to complex systems, embedded systems, you will see every year we get more and more failures. The reason is the complexity, the numbers of lines of code is growing much more faster than the errors per 1,000 lines of code is decreasing. So every year, do you remember, every 10 years, every 10 months, we have twice as much lines of code. So the size in 1,000 lines of code is growing exponentially. So you have much more lines of code, and how many errors do you have in this project is the number of lines of code multiplied by errors divided by 1,000 lines of code. And you will see this number is growing. The total amount of errors which you are having in your system is growing, and it's growing exponentially with time. So the next release, if it is grosser than the previous release, then it will have more errors, more failures, more faults. Well, what is the solution? Tell me by yourself, what is the solution? If complexity is a problem, it's dangerous, the solution is make it simple, okay? It seems to be easy. The key factor for dependability is simplicity. And let people, developer, to choose. Take the simple way and take the complex way. And you will be surprised. I don't know why, but almost all developers take the decision to make it more complex. So if there are two ways how to make it, the simple way or the complex way, most people I don't know why, take the decision to make it more complex because they think it's more elegant. And they learned in the university, it's nice, or in university or the training where they are learning to program, they learn it's nice to make the things elegant. But more elegance is maybe more complexity, and they are doing the thing more complex. And really, I don't know why. They have the choose, they can take the decision, and they take the decision, I will do it more complex. Even if they have to work harder and to develop, to test and debug will be harder and take more time. But they take the decision, complexity. Why is it so difficult to make it things simpler? I was thinking a lot of time. And I have analyzed many students, many professionals, and I found beginners make everything much more complex. They try to include all what they have learned in the university or in the training because they think this is good, and this is good, and if I want to go to do a good system, then I'm going to take everything which is good. So every good things together will make a very good system. That's wrong. Let's take an example of your kitchen. Take a look in your kitchen. You have a lot of things which are good. They taste very good. And then you want to make a very good soup. And then you say, this tastes good, I take it. This tastes good, I take it. This tastes good, I take it. And you mix everything which you consider which is going to taste good. And at the end you expect the soup will be a very nice soup. It will taste very good. Well, and then you were expecting a very delicious soup, but the result is the opposite. It will be incomestible. No one will be able to eat the soup. It will be terrible. Okay. If I take a look to experienced experts, they come closer to the target. They know what they need, and they don't take things which they don't need. And they can remove what is not vital. They are able to recognize what is important, and they can build this, and they are able to recognize what is not important or you will never use, don't use it. Another big mistake here is most people learned in the university or in the training to be ready to let everything in your program to be able to expand. So in case in the future you will need something, then make everything ready to be able to expand the program. But the opposite will be the true. You will never need these things which you have done to increment the program. When you add new functionality, it will be totally different. From the beginning, you are not able to think for everything you will need in the future. So don't do that. Don't try to make everything ready to expand the program. Make it simple, only the things which you need. I would like to tell you an example, my first experience in my first space mission. Well, I got the job to make the program for a satellite, and I wanted to do something very good. Of course, it was my first space mission, and I wanted to make a good impression. So I made a lot of very nice things in the program. I was investing a lot of time doing very nice things which will be very nice in the satellite. And then the system engineer took a look to this and said, what is that? Why did you do that? Why did you do that and that and that? We didn't require it. He showed me the list of requirements, what the satellite shall do, and everything else shall be removed. So they didn't accept my so nice program, which I wanted to use to make a good impression for everything which I have done, rejected. Do only what we need, only what we require, and no single line more. And that was my first experience, and I learned in this moment to focus in what we need and do not add nice to have or things which we don't really need. Here, I would like to show you a remarkable observation. Let's take a look in the Hall of Fame. Very famous, the star software programmers of all times. Let's say the best software developers of all times. For example, Linus Torvalds, the developer of Linux, or Brian Kernighan, the developer of Unix, a very nice operating systems, or Richard Stallman, the founder of GNU, Emacs, and so on, or Donald Knuth, the maker of LaTeX, many people use LaTeX, or Hans Reiser, the maker of the Unix file system, or Dennis Ritchie, he worked on Unix and defined the C language. So almost everyone is using C language. This comes from here. And then let's take a look how they program. Let's take a look in this Hall of Fame. And what we find is surprising, very remarkable. The programs from these famous star programmers are much more simple than the programs from normal programmers. You will expect, if they are such a genius, if they are such a good programmers, their program shall be so complex, no one shall be able to understand this. But it's the opposite. Their programs are really simple. We have developed some metrics to compute the complexity or to measure the complexity of software, is what we are doing to try to reduce your complexity. And according to these metrics, which we are using, we found the complexity of the programs of these people is less than the half of the complexity of normal programmers. And then the next step, going from normal programmers to beginners, then you have factor 10. So, okay, until here, talking about complexity, making things simple. I hope I convince you to try to think simple and to try to go lower on the complexity. And I hope I convince you adding more complexity is dangerous. You are coming to the critical complexity where everything is going to collapse. Well, and now let me give you some recommendations about how to improve the safety of your system. Safety engineering is what I call, or how to improve the dependability of your systems. These are only some recommendations coming from my experience. For sure, you have your own experience, and for sure, you have your own recommendations. Well, for me, it will be very nice to hear your recommendations, how you do it, but let me tell what I can recommend to you. Something important is, these are just recommendations, and there is no systematic. The first thing is, we want to improve the dependability and the safety. We don't want accidents if we are working with safety in critical systems, safety engineering. And this is the case where failure shall not be an option. Because if we have a failure, we have an accident, and in this accident, people might die or something like this. The problem is, failure is not an option, but we cannot avoid the failure. But we are not perfect. And if we are not perfect, we cannot create perfection. So we cannot create perfect systems, we cannot create machines which never fail. Everything which we are going to build will fail like ourselves. Okay, this is something we have to keep in mind. Okay, then some recommendations. In a safety critical systems, we have safety critical functions. Okay, some functions are dangerous, and these functions shall be protected using barriers and interlocks. For example, to access a critical function, first you shall open a barrier. For example, if you have a button, stop the system, emergency stop or something like this, before you press this button, you have to open a door, maybe with a key, and then you can press the button. And for very critical systems, maybe you have 3 buttons which have, or maybe 3 keys or 2 keys from 2 different persons which are very far away from each other, which shall be activated almost at the same time, maybe 1 second difference. Some prepare, release, and then operate. And this is something we can do mechanically and in software. In the safety critical functions systems, we have safety critical commands, functions, and these shall be performed incremental. So for example, let's say we have a satellite, and at the end of line, we shall turn everything from the satellite off, and the satellite is die, or activate the thrusters and send the satellite back to the Earth, and then it will be destroyed when coming back to the atmosphere. And this is something we shall do to avoid the satellite to stay there and perturb other satellites. So there is a command end of life. Or for rockets. When a rocket is flying and if you find something is very wrong and it's a danger, there is a single command for the rocket's end of life. Destroy yourselves and then it will explode. That is of course a critical function, and before you send the command explode or end of life, you shall send previous another command which says release this command. So we know what we are doing, and then you send the command end of life. Not just if you use send the command end of life, this shall be rejected. Okay, then we have to dynamic modify the goals of the system to mitigate damage. Every system has a goal, what it shall do, but if there are damage, is something going wrong, maybe we have a failure, then the goal shall be something different. Not to provide the service anymore, but to reduce the consequences of the failure or maybe of the accident. Total different goals from the previous defined targets of the system. Okay, and then you have managed the resources needed to deal with safety crises so that enough will be available after the emergency. So do not consume all resources when operating, left enough resources to operate the system after the failure and to mitigate the emergency. And something very important, and this is the reason for many accidents, exercise the critical functions of safety features to access and maintain the availability. For example, operators together with this and design the operators interfaces to provide information and power they need to deal with the exceptions. Operators shall be trained to handle the exceptions, and the emergency functionality of the system shall be tested regularly. It's a very big mistake. You create the emergency functionality and this will be never tested because you don't need it. The system is working properly and the operators are not ready to use it. They are not trained, or maybe they were trained years ago, and at the moment of the emergency they don't know anymore. They have forgotten how to activate this functionality, or this functionality, it was tested several years ago and now when you need it, it doesn't work anymore. So this is something which shall be performed periodically. And now something very important, now if everything is interconnected to internet, so malicious attacks may occur, so you shall protect your systems against hackers and malintentions and malicious attacks. For example, use cryptology to sending commands and getting telemetry, some kind of identification who is controlling the system. Okay, and something very important, ironically, disasters contribute more to future safety than success stories. So from all systems which are working properly, we say, okay, working. But the best improvement we can do is after an accident. If we have an accident, then we can collect this information, what occurs, and from this accident we can learn to correct this to make it better. So from accident to accident, we are improving of dependability. The problem is this is only one point. The reason of this accident will be improved, so the same kind of accident will not occur, but there are many others. So we have to have many accidents until we have covered everything. And the problem is there are so many combinations or so many events which we cannot think in advance. So when it occurs, then we know, it was possible. Because an accident is not only one event, it's a very long chain of events. And we are not able to think on all combinations of events or all chains of events. So in everything which we do, there will be a gap, and this shall be detected after experience of the accident. This is why it is so important to get the black box of an aeroplane after an accident. Let's see some examples. Years ago, this aeroplane from Air France 477, which crashed in the Atlantic, and no one knew why. They were searching for the black box 1 year in 5-kilometer depth, and the cost was at 100 million euros. Why they invest so much? Or this Air Malaysia, I think they never found the black box, I'm not sure anymore, but they were searching for 2 years. And they invested about 100 million euros in this search, and I think it was not found, the black box. So it's not possible to reconstruct what was the reason. So we are ready to invest so much money finding the black box only to find the reason and improve the system for the next time to avoid the same type of accidents. Okay, some other recommendations from me. We shall know for every system which we shall do, it will crash. So it doesn't matter what you do, the system will crash. The only question is when. When it will crash. This is something we don't know. This will be the surprise. And the second is, will be ready to handle the crash. And the problem is, if you are investing all your resources to avoid the crash, then you will not be ready to handle the crash. And you have invested wrong, because I can assure you, you cannot avoid the crash. It will crash, and therefore it's more important than investing to avoid the crash, invest to be able to handle this crash, because it will come. And if you are not ready, then we will have the accident. This is how it works. We have the system startups, then the system works properly for a time, and then we have the crash. Maybe we have a recovery time, and then the system can continue working properly. Then the most important thing is, if we know this is going to occur, then we shall be able to recover the system and continue working as soon as possible. Maybe using redundancy to avoid a failure from outside. For example, we implement, or I recommend, ultra-fast recovery. Much more important than prolonging this shall be to reduce this time to recover. If this time to recovery is 0, for example, is an extreme which you cannot get, then this is the best you can do. The system might crash at any time, once per second, and the recovery is instantaneous, so from outside you don't see any failure. But a recovery time of 0 is not possible. Then we need some kind of fault tolerance, redundancy. Let's assume we have two independent systems. They shall not have a common failure, because if they have a common cause failure, they are going to fail and crash at the same time, and then you have win nothing. Okay, let's assume they are independent and they are working properly for a time. Then we have a crash. First, we have a ultra-fast recovery to have as soon as possible the required redundancy to continue working. So from outside you don't see the failure, because here this keep control. And let's assume this time to recover is very long. Then we have here a crash. It has a very long time to recover, and then the probability on another crash from the redundant system in this time is increasing together with this time to recovery. And then this can be an accident. This is a period of time without control. Both control have failed in this same period. So it's much important, which I recommend, it's important to keep this time of working properly, availability as long as possible, reliability as long as possible, but I will recommend take care of this time of recovery, reduce this time to recover. Okay, and what I will recommend for ultra-fast recovery to reduce this time is you shall have minimal context. So the communication or the context to restart the system shall be minimal. If you have to recover millions of bytes or megabytes, then it will take a long time. Distribute the context of every application permanently and replicate the context. So if one application or one node fails, other node has enough information to continue working at the same point. Or best, try to create a contextless or stateless communication, not only communication, control. So if you don't have to know the whole history, then you can take a look to the current state of the system and take control immediately. If you need a lot of information from the past, then the recovery is going to take long, because you have first to synchronize your system. Okay, do not make a hardware test. Get to work as soon as possible. And after wake up, you can begin working very fast if you don't have to recover the history. Okay, and continue, no hardware reset, go to work as soon as possible, very fast boot, so the booter shall be instantaneously jump to the control routine and do nothing more. And then if you wake up, first listen what is going on, And then when you have synchronized your state, your contact, you can begin talking, sending messages. But first, listen, synchronize, and communicate. Another is, I will recommend, the computer is not the most important part where you have to invest to get the dependability. The most important part is the network, the communication. Because not the computer is important, but the network, then we are talking about network-centric computing. This is the name which I use for what we are doing. We invest effort to keep the communication network working. Computers may fail, it doesn't matter, as long as we can recover. Okay, but if the network fails, then everything has failed. We need redundancy in the network and the dependability in the network. Okay, then find the minimal component which shall be dependable, and that is the network, and everything else can fail as long as recovery is possible. And concentrate the effort to increase the dependability of the network and let the computer crash. So the rest can be considered as not dependable. Of course, you have to use redundancy. If you know everything is going to crash, then you have to have redundancy, but don't worry. But keep the communication and the network running all time. Something like this. We have many computers, redundant computers, and we can say let them crash, let them fail whenever they want. But the only thing which shall be working permanently is the network. Of course, as said before, it has to be redundant. You have to have at least two networks working at the same time. For inter-node, intercomputer, and computers or computing nodes and devices, and maybe from device to device. Third, to handle the symptom is not the cure. So if you are sick, if you have headache, the cure is not to take something against your headache. The cure is to find what is the reason for the headache and cure this. And I said before, the illness is the complexity. That's the problem. Not the failures you get due to the complexity and you try to handle the failures. No, handle the illness, and the illness is the complexity. What I said before at the beginning of this video, eliminate the complexity. Our target is the irreducible complexity. Reduce the complexity as much as possible. Keep it simple, what I said before. Okay, my recommendations, let it crash. You cannot avoid it. Be ready to handle. Provide ultra-fast recovery. Keep the network working. Most important than more computers. And keep it simple. Better handling the complexity. I mean better than handle the complexity is to eliminate it. Target the irreducible complexity. Okay, and I think this video is already too long, so we are going to stop here. Then see you in the next video.